Hi, my name is Eng Huat, and I lead the magnetic sensor development in Global Foundries. For this IEEE sensor conference, I'm going to share with you the first Foundry 3D Hall sensor for system-on-chip integration. This is an overview of my presentation. First, I will introduce Global Foundry technology and our modular 3D Hall sensor. This is followed by discussion on optimizing the planar and vertical sensors. And finally, I will conclude with a summary of this work. The magnetic Hall sensor have a wide range of applications, ranging from position sensing to current sensing. And they are well suited to be integrated with Global Foundry's smart power technology, which have a wide range of voltages and nodes for various applications like mobility, AC/DC, and automotive industrial. The Hall sensor are then introduced as added features from 180 nanometer down to 55 nanometer. Currently, planar 1D Hall sensor are available, and the 3D Hall sensor will be introduced in this work. So in this work, we introduce the modular 3D Hall sensor to detect magnetic field in 3 directions. Unlike most standalone Hall sensor in the market, it is CMOS integrated, which allows for single chip and multi-functionality. In addition, it requires a minimum mass adder, and the modular design allows independent optimization, mix and match of different planar and vertical Hall elements, thus giving customer the design flexibility they need. For this to work, it will need to sense the 3 Hall voltages corresponding to the 3 magnetic field directions. For magnetic field perpendicular to the silicon surface, we use this planar Hall sensor. A voltage or current is biased to flow from the left to the right, and the Hall voltage is Vz is given by the potential difference between A and B. For in-plane magnetic field, we use the vertical devices at the 2 sides. Current is biased from the outer contact to the center contact. With the y direction magnetic field, the Hall voltage Vy will be given by Vc minus Vd. This is similar for the x direction vertical Hall sensor, giving us the Hall voltage Vx. As such, the 3 sensors together will enable 3D sensing. And we fabricated the 3D sensor on silicon substrate with Global Foundry's 180 BCD light technology. Almost all implants comes from an existing baseline process, except for the Hall layer implant. We could have N Hall 1 for the planar device and N Hall 2 for the vertical devices. In some instances, they could be combined into one single implant. And since the 3D Hall is modular, we can engineer individual components separately. And that is why we start off with the planar module. So to determine how good the sensor is, there are 3 important parameters. First will be the unwanted offset voltage. It is the Hall voltage at 0 magnetic field, which ideally should be 0 if the 4 diagonal resistors are matched. Next, we have the current sensitivity, SI, which is the Hall voltage when you apply the current and magnetic field. This will depend on the doping and the thickness of this Hall layer. And this is for optimizing high SI sensor, which is normally used as a switch. Last but not least, the voltage sensitivity, SV. This is the Hall voltage as a function of voltage and magnetic field. And this will depend on mobility and the number of squares. And this is for optimizing SV sensor for linear sensing and current monitoring. So let's first start with offset voltages. So the plot here shows the Hall voltage as a function of the magnetic field. For the POR 110 channel-oriented Hall devices in red, and 45 degrees rotated 100 Hall devices in green. Both devices have a comparable sensitivity. By rotating 45 degrees, the channel current is now in the 100 direction. However, the diagonal resistors are in the 110 directions. So this becomes less sensitive to stress and process variation. As such, the offset variation here is reduced by more than 50%, thus improving the sensing margin. And this could be further improved by adopting a circuit technique known as the current spinning method, which is shown in this slide over here. So by rotating the current direction 4 times at the circuit level, each time with a 90-degree rotation, 4 offset in various direction and polarity are measured. And when we sum them all up, they cancel each other. And the final offset, which we call the residue voltage, is reduced by 2 orders to less than 6 microvolt. So in this way, we can ensure that whatever we detect is the actual Hall voltage that is modulated by the magnetic field, and not something that is confounded by the intrinsic offset voltage. So what this gives us is a much larger sensing margin. And with this offset voltage resolved, we can proceed to optimize the SI by engineering the N-Hall layer. We experimented with different implants in the process. So the key is by engineering the doping and also the thickness over here, we are able to increase the SI significantly by 2 to 4 times. And for optimizing SV, the cross shape is now replaced with the square shape. And we reduce the doping over here significantly so as to improve the carrier mobility. And what this does is it actually improve SV by more than 2 times. So in short, for the planar Hall module, there are 2 design options which are optimized for SI or SV. And this is to cater for low power and high sensitivity applications. So SI sensor employs a 45-degree rotated cross-shape design and help to achieve a competitive SI of about 385, which is 20% higher than benchmark. And as for the SV optimized sensor, it adopts the square shaped, and the doping in the layer is actually reduced significantly so that it can achieve a high SV of 61 millivolt, which is 35% higher than the target. So both of these planar sensors are now being offered as a 1D sensor and could also be easily integrated as part of the 3D sensor. And with this best-in-class performance, our focus now turns to the vertical Hall sensor. So in the vertical Hall sensor, to detect the magnetic field implant, we consider 2 designs. So we have design 1, which has 5 contacts over here, and design 2, which comprises of 4 blocks of 3 contacts each. And for these devices, we face the same kind of challenges in terms of offset and sensitivity. So, however, one of the key advantage of this modular design is that the doping profile of the vertical Hall sensor could be very different from the planar Hall sensor. So as shown in this Hall voltage versus magnetic field, if we are going to use the vertical Hall device with the scheme 1 planar Hall doping, we are able to achieve the sensitivity as shown in blue. However, if we have the choice to optimize the vertical Hall sensor with scheme 2, we are able to improve that sensitivity by more than 70%. So with this further optimizations, the designer is now able to choose either from vertical Hall design 1 or design 2. So as shown in this slide over here, so vertical Hall design 1 has a much higher sensitivity about 50% higher than Design 2. However, it also comes with the trade-off of 80% higher offset voltage. And this is due to the fact that Design 1 has an asymmetrical structure. So the junction well at C1 is different from those of C2 to C4, which result in a mismatched resistors. For Design 2, it has a symmetrical structure and hence a lower offset voltage. However, due to the extra current path or extra parasitic resistance, the sensitivity is reduced significantly. So in summary, the final choice between the two will depend on the product design requirement. And combining this vertical Hall sensor with the planar Hall sensor, we are able to detect magnetic field in the 3 directions. So to conclude, in summary, we demonstrated the first Foundry 3D silicon Hall sensor technology, which is fully integrated into GlobalFoundries 180 BC Lite process. So the modular approach allows for design flexibility to integrate different options of planar and vertical Hall devices into a 3D Hall sensor. And last but not least, excellent sensitivities are achieved at minimum cost. And that concludes my presentation, and thank you for your attention.